Neutrons, the neutral building blocks of atoms, have long puzzled scientists with a simple yet confounding question. How long do they live, once free from the nucleus? Two experimental methods yield lifetimes differing by about 10 seconds, a discrepancy that has defied explanation for decades. Now, a revolutionary theory proposes an unseen player, an invisible form of hydrogen that could not only resolve this neutron lifetime puzzle, but also illuminate the dark matter enigma, an elusive mystery that's haunted physics for nearly a century. The smallest inconsistencies often point toward the biggest breakthroughs. And this one might rewrite the rules of what we think is visible in the universe. The neutron lifetime discrepancy isn't just a trivial measurement error. It's a significant anomaly that challenges our understanding of fundamental physics. Beam experiments suggest free neutrons decay in about 888 seconds, while bottle experiments indicate a shorter lifespan of approximately 878 seconds. This 10-second gap exceeds experimental uncertainties and hints at physics beyond the standard model. This means that one of the most basic constants of matter, how long a neutron lives, depends on how we observe it. That's not just strange, it's profound. If neutrons are vanishing into unknown states, this raises a profound possibility. There may be decay pathways we've never detected, perhaps into invisible matter, into hidden sectors of the universe itself. Resolving this puzzle is crucial as it impacts our comprehension of particle interactions and the evolution of the early universe. It also poses broader questions. Are there hidden particles or unknown forces subtly influencing the most basic components of matter? And could these effects hold the key to understanding the nature of the cosmos itself? This isn't just a matter of solving a quirky footnote in particle physics. It touches the foundations of everything from nuclear energy to astrophysical processes. It means that the way we model atomic behavior across nuclear reactors, star formation, and even the Big Bang might be missing a critical variable. Enter Dr. Eugene Oakes, a theoretical physicist at Auburn University, who has proposed a compelling and unconventional solution published in the journal Nuclear Physics B in May 2025. Oakes revisits the possibility of a two-body decay mode for neutrons, where a neutron decays into a hydrogen atom and a neutrino, bypassing the typical three-particle decay involving a proton, electron, and antineutrino. Historically, this two-body decay was considered exceedingly rare, occurring in only about 4 out of every million decays. So infrequent it was often dismissed in modeling. However, Oakes argues that previous calculations overlooked a critical factor: the existence of a second, invisible flavor of hydrogen. This isn't just a hypothetical tweak. It's a radical reinterpretation of how the hydrogen atom itself might behave under extreme quantum conditions. This hypothesized form of hydrogen doesn't interact with light, rendering it invisible to conventional detection methods. It would behave like hydrogen in terms of mass and composition, but would be undetectable through the electromagnetic spectrum, our primary means of observing the universe. This theory is especially intriguing because it doesn't require rewriting the entire framework of physics. Instead, it suggests a blind spot, a solution hiding in plain sight, masked by assumptions in atomic theory. Oakes suggests that if neutrons decay into this dark hydrogen and a neutrino, the decay would go unnoticed in beam experiments, which detect decay products like protons. In contrast, bottle experiments count the remaining neutrons, capturing all decay modes, including those into invisible hydrogen. This discrepancy could explain the differing neutron lifetimes observed. In his analysis, Oakes draws on earlier theoretical work surrounding bound states in hydrogen atoms, areas typically regarded as solved. But by challenging the assumption that the proton is a point-like particle and accounting for its extended structure, he finds new energy states that were previously dismissed or considered physically irrelevant. These forgotten solutions, he proposes, may be the key to unlocking a new atomic configuration, one hidden in the folds of equations we've trusted for a century. To bolster his case, Oakes integrates previous particle physics models with quantum electrodynamics, proposing that dark hydrogen forms under specific constraints of the Dirac equation, a cornerstone of modern quantum theory. The idea is not only elegant but also testable, providing a new experimental target that physicists can pursue. If proven, this could represent one of the first known transitions of matter into a dark form, without invoking any new particles beyond the standard model. Delving deeper, Oakes employs the Dirac equation, a fundamental equation in quantum mechanics, to describe the behavior of electrons in hydrogen. By accounting for the finite size of the proton, a correction often negligible in ordinary conditions, he uncovers a solution where the electron in the hydrogen atom is tightly bound to the proton. This extremely compressed state results in a configuration that doesn't emit or absorb electromagnetic radiation. This dark hydrogen would be invisible to our instruments, yet it could be a common product of neutron decay. This result isn't just a mathematical curiosity, it challenges one of the most well-studied atoms in science. The hydrogen atom has been foundational to everything from quantum mechanics to cosmology. But now, Oakes suggests there may be an entirely different form of hydrogen that has simply evaded detection for all of human history. In most hydrogen atoms, the electron's orbit allows for photon emission or absorption, visible as spectral lines that are used in everything from cosmology to medical imaging. But in this dark variant, the tight binding alters the atom's quantum state so significantly that it becomes electromagnetically silent. Such atoms wouldn't glow, reflect, or absorb light. They would drift silently, undetected, through even the most sensitive telescopes, ghostly relics of a hidden subatomic process. Oakes calculates that this two-body decay into dark hydrogen could be about 3,000 times more likely than previously thought, occurring in roughly 1% of all neutron decays. This frequency is sufficient to account for the 10-second discrepancy between beam and bottle experiments. Moreover, the existence of dark hydrogen could have profound implications beyond neutron decay. If just 1% of all neutrons are disappearing into dark atoms, we may be vastly underestimating the role they play in both terrestrial and cosmic physics. In a 2020 study, Oakes proposed that dark hydrogen could explain an unexpected dip in ancient hydrogen radio signals observed by astronomers using the EDGES experiment, an anomaly that couldn't be accounted for by known physics. This signal, which dates back to the cosmic dawn, was weaker than expected, hinting that something invisible was cooling the hydrogen gas. Oakes suggested that dark hydrogen could be the culprit, siphoning off energy and drifting undetected through the early universe. Unlike other dark matter candidates that require entirely new particles or untested interactions, such as supersymmetric WIMPs or axions, dark hydrogen fits within the existing framework of quantum mechanics and the standard model. It's a simpler, more intuitive possibility. As Oakes noted in a statement, the appeal of this theory is that it doesn't require introducing exotic new particles. It's a reinterpretation of existing physics that has simply gone unnoticed until now. And that's perhaps the most unsettling part. The idea that the universe has been whispering its secrets all along, but we've been looking in the wrong direction. The implications of Oakes's theory are vast and deeply interdisciplinary. If dark hydrogen exists, it could not only resolve the neutron lifetime puzzle, but also provide a tangible, testable candidate for dark matter, which constitutes about 85% of the universe's mass. This would bridge the gap between particle physics and cosmology, offering insights into the early universe's composition, thermal history, and structure formation. It would also unify two long-standing scientific mysteries, neutron decay and dark matter under one coherent framework. To test this theory, precision experiments are underway at Los Alamos National Laboratory in New Mexico and Forschungszentrum Jülich in Germany. These efforts represent a global push to detect what may be an entire hidden layer of atomic structure. The approach: bombard hydrogen with electron beams and observe the resulting spectrum. If dark hydrogen exists, it may subtly alter the decay dynamics or reveal itself through a statistical anomaly. Subsequent steps involve stripping away ordinary hydrogen atoms using lasers or electric fields, leaving behind only what doesn't interact, what doesn't fluoresce, and what shouldn't be there. Detecting this invisible hydrogen wouldn't be straightforward. It would involve observing what doesn't happen. The absence of expected interactions or the presence of unexplained mass or energy loss could serve as the first indirect signs of its presence. If even one experiment confirms its existence, it would mark a turning point in modern physics, akin to the discovery of the Higgs boson, but potentially even more transformative. A silent atom, a missing signal, and the potential to finally see what has never been seen. The neutron lifetime puzzle has perplexed scientists for decades, but the introduction of dark hydrogen offers a promising solution that aligns with existing physics frameworks. By potentially resolving this anomaly and providing a viable dark matter candidate, Ox's theory could reshape our understanding of fundamental particles, cosmic history, and the very architecture of matter itself. As experiments progress and the physics community scrutinizes this theory further, we may soon witness one of the most exciting scientific breakthroughs of the century. Is the key to dark matter not hidden in exotic particles or parallel dimensions, but quietly lurking inside the humble neutron? Subscribe now and join us as we explore this and other frontiers of real, cutting-edge science.